not necessarily coordinate, you know, of anything. It's just the two numbers given. We call it a vector, right? Ordered pair vector. And a new operation is defined. R is not a vector here. R is a number. You can call R as a vector. Vectors, everything is a vector in mathematics. R is a number, and then you can multiply number to this ordered pair. And this is how you do it. This number is multiplied to the individual part, right? Very simple operation, easy to learn, right? Whatever the context is this is coming from, that's the straightforward definition of mathematics. It's given. So let's look at next one. What are they calling here? That number in that context of a vector is called scalar. Scaling is that you have an object in the computer software. Often you can grab it and scale, bigger and smaller. That's scalar here, and we call that scalar multiplication, not scalar product. Scalar product means something else. So you have to use word scalar multiplication. You can multiply number to a vector. Vector is not necessarily a number, more complicated object entity. Good. Scalar multiplication. That our number R can be negative as well. So what you see here is an ordered pair 2, -3 as a vector and scalar multiplication 4. Then you know what to do that, right? And here's a second ordered pair and scalar multiplication. That's probably the second thing you have to do. I'm talking about order of operation, right? Then once you figure that out, and then you add something you practiced yesterday, right? And here's another problem here. What is the order of operation here is emphasized. You add these two vectors first, right? Then do the scalar multiplication later. That's the idea about this problem, right? I think this definition is very simple. You can do this thing on your own. And especially they use this bracket. This is very old-fashioned. These days, they all use consistently parentheses. Very confusing. Bracket could mean something else in these days. So I'll be using the bigger parentheses. Right? So I want you to copy that problem down, and once you finish that copying the problem, then you do that problem on your own, and I'll be writing down solution here, right? I'm going to write it like this. This is our official exercise number 1 today. So you name those exercises. The whole thing is 2 points. This is 1 point you get. This is another 1 point you get. No partial credit, just 1 or 0 for each part. Alright, was that okay? What's the lesson? These two things connected, right? Not separate. They're all same numbers in different order of operation, right? And it turns out they're the same thing, right? Of course, it turns out the same thing for these two, but would you believe that it's going to be always true? This is actually always true. If you do this over operation with this number, it's always true. The question is that how are you going to convince yourself? Is there some insightful way to understand this one, or are we going to just write down A and B and C and D and E and F and do this straightforward calculation and show that these two things are the same? That's the second, latter one is the preferred method of mathematicians. Don't think too much about it. It's simple enough. Just do the calculation, show left-hand side is equal to the right-hand side, right? Just straightforward algebraic calculation. So we'll do that. We'll just accept it that way. These two things always equal to each other. So let's write that down. I have a scalar R, right? Scalar R as a remark. Let's conclude this exercise. Scalar R is multiplied to one vector, right? How do you write vector in physics and mathematics? Boldface, or in type here we're going to use vector V with arrow. Is that okay? Yeah. It's easier. I can't do boldface here. So arrow is going to be, this is a vector. And the same scalar, different vector W. This V bar, this is so annoying. So once I declare the V bar the vector, I'll use just V. And you understand, oh, that's the same V, so it's a vector. So I don't use arrow all the time. Hope that's okay. Is equal to, right hand side was actually you add this 2 vector first. It's a statement, so I'll use vector correctly. Then multiply the same scalar later. Then they are saying these are always equal to each other, right? What is this law called? Remember this type of a law? Distribution law, distributive law, right? So we just justify the distributive law holds for vectors and scalar multiplication as well. Does that make sense? That's what that is. Yes? W is a different vector, thank you. So like this one, 2, -3, 3, 5, that's a 2 different ordered pair, 2 different vectors, right? Yeah. Any other question? All right. So they're asking you to show that A is a number scalar, and we have A1 and A2. Those are 2 ordered pairs. So those are the 2 vectors, right? They set it so they don't have to use boldface or anything. They set it as ordered pairs. So you understand this is capital A and is ordered pairs of vectors. So they stated like exactly like that. You add first and scalar multiplication later. Scalar multiplication first and add later. They're always equal to each other, right? So how do you show this thing is true? Is it enough to just use an example? No, right? You have to show that in the general. So this is how you can do it. If this is a problem, if they ask you to prove this one, sometimes the picture is not enough. Picture never represent the general situation. It's just only about one thing. So how is it the proof goes? It's not solution. It's ask you to show you. You prove it. So A is general enough. A1, capital A1, have been broken down to ordered pairs. So you're going to write A1 as X1, Y1. Is that all right? So that's an ordered pair, right? Down to component part, X1 and Y1. And A2 is going to be X2, Y2, right? Correct? And then you compute the left-hand side. And then you write down the left-hand side, LHS, is equal to this ordered, computed first. A is later. If you add these 2 vectors, you get x1, x2, y1 plus y2, right? Isn't that the left-hand side? Then you can multiply scalar multiple inside there. Then you can distribute further because we've learned the distributive law for numbers, right? So I'm not using the distributive law you're asked to prove here. I'm using the distributive law in the level of numbers. I distributed A inside and here and there, right? Okay, so this is true. And what is the right-hand side? You do this operation first, so that's going to be A times x1, A times y1. If you multiply A to this vector, I hope you see that, right? And plus, A is multiplied to the second vector, there's A y1, x2, B y2. Then you add these two, AX1 plus AX2, AY1 plus AY2. There's no B in there, sorry about that. There's all A. And then you recognize, oh, I show that this left-hand side and right-hand side turn out to be equal to each other. We didn't quite understand anything. I did just correct calculation. At the end, they were true. They were equal to each other for all the general cases. So they declared this is a proof. I don't know if you understood anything or not. This is a correct proof. That's what sometimes mathematicians do. All right? Okay, what's the point? It's very tedious. It seems like this really silly thing that I just did. What you have to pay attention to here is logical structure. Why did they make this big deal out of this? It's because it's not obvious if you really think about it. Order of operation. If you enter new entities, you have to think about it. Right? In many cases, order of operation matters. Any question? This wasn't an exercise, right? Yeah. I declared as exercise number 2, and that goes into the sheet. But it's okay if you wrote it down. All right, this is a little bit more involved exercise. This is something you have to think about. The A is easy, so that's going to be your second exercise. The B is going to be the separate exercise but it is a little bit a more advanced question. So let's do this one. I want to copy this one down. Exercise number 2. Find real numbers a1, a2, a3 such that this sum of 3 scalar multiplications become 5, 6. Don't think that he didn't really teach us anything like this. You have to use your logical thinking and proceed, right? We don't know a1, a2, a3, and what can I do about left-hand side? So that you can compare this one to the right-hand side, right? Maybe we can call that as simplifying. Can you simplify left-hand side down to one single ordered pair? Then maybe you can compare that with the right-hand side, right? One ordered pair compared to another ordered pair, each component must be the same. Each entries must be the same, right? Any question about that instruction I just gave you? Yes? Well, it didn't seem it was that easy, was it? So let's begin from left-hand side. When you simplify left-hand side, you get this sum of 3 things as a first entry, and this sum of 3 things in the second entry. That's one vector, one ordered pair, right? Did you get that part right? And this is supposed to be equal to the right-hand side, which is 5, 6, right? 5, 6. So first entry must be 5, second entry must be 6. Any 3 numbers that satisfy this one will be one answer. You go out and, let's try this one and that without using the consistent mathematical method to reduce this one down to an equation. You can do that since that was a question, but I tried a more consistent way. So here I noticed that we have 3 variables, right? And 2 equations. If you have 2 equations and 2 variables, it's usually, you expect that there is a concrete solution. But if you have more variable and fewer equations, you usually have a free one variable in there. So I looked at A3, that's easy. So I decided to just plug in A3 equals 0 and 0, 0. If I plug in A3 equals 0 because it's free, I think, free is 0, then you end up at 2 equations and 2 variables, A1 and A2, right? So you probably know how to solve that 2 by 2 equation. So that's what I was trying to do. But I end up in a weird problem. If I plug in A3, 0, then I have this equation and that equation. Then you eliminate, substitute whatever the method you try to use. I multiply 3 here so that I can eliminate this one. So I multiply 3A1 and 6A2 here as you multiply 3 there. So 3 there makes it 18. Now if you try to eliminate that, that was our purpose, but that also eliminates this one as well. You end up at 0 equals negative 13. That's not true, right? That means that A3 didn't work. So I chose the wrong variable actually. If you choose A2 being 0 and solve it here, then it might have worked. Right? So what I did is that, okay, realized A3 was actually the problem spot, which I didn't see at the beginning. So why don't I solve this more in general? So I move that one aside here, treat it as if it's a constant, and solve this one just like I did it here. And then you encounter this inconsistency that if you multiply, you have 5 plus A3, 18 minus 3 times A3. Left-hand side, as you eliminate, becomes just a 0. So this better be equal to each other so that it's 0 equals 0. So I set it here. Okay, this 5 plus A3, 18 minus 3 times A3 must be equal to each other. So that this is consistent, not like this inconsistent here. So I said equal to each other, and A3 must be 13 over 4. Right? So I got that A2, A3 being 13 over 4. Go back to this equation. I plug in A3 into 13 over 4. And for example, if you look at it here, then you get this equation. 6 minus 13 over 4, that's 11 over 4. 11 over 4. So you get that equation. And if you plug in 13 over 4 here, you get another equation, but you will find that that's exactly the same equation, because they are kind of the same equation except the right-hand side. So from here, you're really free, and because this equation and the other equation will essentially give you the same equation, you can plug in easy value. A2 equals 0, A1, you solve for it, and then it's 11 over 4. So I claim that these three numbers still works for the first part as well. So this is one answer, but I think A3 should be 13 over 4. There's no other choice for A3. Yeah. Right? One tough problem? Any question? It could have been a lot easier than this. Right? Is that okay? Yes. Right, the matrices, that you can do that. You can reduce the matrix if you do out of the linear algebra, then it actually exhibit all the solution perfectly, right? Not just one in here. Yeah. But this course doesn't require matrix theory, so I didn't do that in here. But that's right, it's correct. So what is the second question is saying? Is the solution in part A unique? Is there only one solution? We just discussed that. It can be more than one solution, right? So let me do that in here. So remark. At the end, we said that is A3 has to be 13 over 4, but I was saying A1 and A2, it can be different, right? So here, if I choose A2 equals 1, then you get this equation A1 plus 2 times 1 equals 11 over 4. So that's A1. If you subtract 8, so that's 3 over 4. Is that right? If you subtract 2 from 11, that's 8 minus 2. I think it's 3. So A1 is 3 over 4, A2 being 1, A3 being 13 over 4. I claim that if you plug in these three numbers here and there, these two things are satisfied. Again, if you choose A2 being something else, pi, for example, and if you plug it in here, solve for that, that three number still satisfies this equation. And so on. So that kind of answers the second part. There is no unique solution. These two triples of numbers satisfy these two equations originally given. Okay? It's asking you, can you find A1, A2, A3 that are integers? That is, this type of question is not very important in this course, so I'm going to skip it. But you can actually find one solution that, well, actually we answered it here, right? A3 must be, had no choice. It has to be 13 over 4, so I guess the answer is no, right? So let me show you this one. And any question that might came to you at this point?